Good day, dear participants of conference. Today I want to talk you about our joint work with Anatoly Kondratyev on finite groups, which Gruenberg-Kegel graphs are isomorphic to the pore. Our notation and terminology are mostly standard and can be found in atlas of finite groups. Now I will give some necessary definitions. So let G be a finite group, denoted by pi of G, the set of all prime divisors of the order of G. And if order of pi of G is equal to n, then G is called n primary. The Gruenberg-Kegel graph or prime graph gamma of G is a graph with the vertex set pi of G in which two distinct vertices P and Q are adjacent if and only if there exists an element of order pi Q in G. The next block of definitions is about different type of largest normal subgroup of G. The first definition is about S of G, is a solvable radical of G. In other words, is a maximal solvable normal subgroup of G. O of G is the maximal normal subgroup G with odd order. And OP of G is the maximal normal subgroup G, order of which is equal to a power P. Now I want to talk a few words about motivation. In these two works, Anatoly Kondratyev described finite groups with Gruenberg-Kegel graphs as Gruenberg-Kegel graphs of group out Yanka-2 and A10, respectively. In this slide shows the Gruenberg-Kegel graph of out Yanka-2 and A10, respectively. This in the Gruenberg-Kegel graph of out of these groups differ only in the positions that vertices 2 and 3 occupy in them. In the Gruenberg-Kegel graph of out Yanka-2, vertex 2 have a power 3 and vertex 3 have a power 2. And in the Gruenberg-Kegel graph of A10, vertex 3 have a power 3 and vertex 2 have a power 2. Thus, Gruenberg-Kegel graphs of these groups as abstract graphs are isomorphic to the pore, having the following form. The group A10 is interesting for us because it is a group with small numbers of prime divisors, and only this group has the connected Gruenberg-Kegel graph among all four primary simple groups of atlas of finite groups. So we part a natural general problem to describe finite groups which Gruenberg-Kegel graphs as abstract graphs are isomorphic to the pore, where R, S, P, and Q are some pairwise distinct primes. And we will use this notation for the vertices of the Po throughout our talk. The structure of solving this problem consists of three big steps. The first step was to study the case when the group G is almost simple. The second step was to study the case when the group G is non-solvable, and the third step was to study the case when the group G is solvable. On this moment, the first step is finished, the second step in progress, and the third step is the subject of future investigations. So about first step of this research. Let me remind you that group G is called almost simple if G is was between some non-abelian simple group G0 and out of G0. In studying this case, the results described in the following two works of Anatoly Kondratyev and Igor Khamtsov turned out to be very useful for us. In the first work, what described Gruenberg-Kegel graphs of finite, almost simple three primary groups. Very interesting that only out A6 and out U42 have a connected Gruenberg-Kegel graph amongst almost simple three primary groups. And in the second work was described finite almost simple four primary groups with disconnected Gruenberg-Kegel graph. Also in these works was described the normal structures, some three primary and four primary finite groups. This result turned out to be very useful for further investigation of our general problem. So, in our joint work with Anatoly Kondratyev, proved that if G is a finite non-solvable group and graph gamma of G as abstract graph is isomorphic to the Po, then the quotient group G by S of G is almost simple and classified all finite almost simple groups, which the Gruenberg-Kegel graphs as abstract graphs are isomorphic to subgraphs of the Po. Now I want to tell about our results in second step of this investigation. The first results is about a group without elements of order 3, and in this case, normal structure of G is known. Without elements of order 3 and gamma of G as abstract graph is isomorphic to the Po. Then normal structure of G is known. The second result is natural continuation of first theorem. Let G be a finite non-solvable groups without elements of order 6 such that 3 divides order of G and gamma of G as abstract graph is isomorphic to the Po. Then normal structure of G is known. theorem 1 and theorem 2 together was described non-solvable group G without elements of order 6. And gamma of G as abstract graph is isomorphic to the PO. So the third results. Let G be a finite non-solvable groups. Q divides order of S of G. Remember that S of G is a solvable radical of G. And gamma of G as abstract graph is isomorphic to the PO. Then normal structure of G is known. And the last results, which now is in progress. Let G be a finite non-solvable group such that gamma of G as abstract graph is isomorphic to the PO with a vertex of order 1 less or equal 3. Then normal structure of G is known. After this, we will research the next two cases. The first case is elements of P more or equal to 5, and group G have element of 6. Then R and S is a pair 2 and 5. And the last case, if R and P is a pair numbers 2 and 3. Now I want to tell about this result more details. The first result, so let G be a finite non-solvable group. If 3 does not divide order of G, and the graph gamma of G as abstract graph is isomorphic to the PO. Then there are four possibility. The first possibility is G dash is Suzuki 8, R equal to pair P and S equal to pair 5 and 7, Q equal certain P of S of G is pair 2 and P, and every two chief factor of G as a G dash model is isomorphic to 4-dimensional or 16-dimensional irreducible Suzuki 8 modular. Moreover, the second possibility always appears. And this possibility realized for groups following shapes. And you can see on this slide a Gruenberg-Kegel graph of this group. The second possibility is G dash is out Suzuki 32, and condition on numbers R, S, P, Q, and normal structure of G you can see on this slide. And this possibility realized for a group such shape. And we can see Gruenberg-Kegel graph of such groups for P equal to 31. The second possibility, G dash is equal to one of following groups. The condition on numbers RP, SQ, and normal structure of G you can see on this slide, and this possibility realized for groups following forms. And we can see Gruenberg-Kegel graphs of such groups for p equal to 31. And the last possibilities, G dash is equal to Suzuki 8, and condition on numbers RSPQ and normal structure of G you can see on this slide. And these possibilities relies on the group following shape. And we can see the Gruenberg-Kegel graph of this group on this slide. Before moving on to the next result, let's say a few words about classification of finite groups without elements of order 6, because this classification turned out to be very useful for getting it. In 1977, in 3 papers by Padufalov, by Gordon, and by Fletcher, Selmacher, and Stewart, finite simple groups without elements of order 6 were determined independently. In this article, we described all finite simple groups without elements of order 6. For the next results, the following theorems from this work is especially important. Let G be a finite non-solvable group such that 3 divides order of G. Then G does not contain elements of order 6 if and only if G have the following normal structure of G, which you can see on this slide. The second result, let G be a finite non-solvable group without elements of order 6 such that 3 divides order of G and gamma of G as abstract graph is isomorphic to the pore. Then there exist 3 cases. The first case, Q equal to and G dash is L to 2 power n, and a normal structure of G you can see on this slide. For this case, there exist 2 possibilities. The possibility 1, n equals 4, p equal to 17, and pair R and S is equal to pair 3, 5. This possibility realized for the direct product of a cyclic group of order 17 and L2 16. You can see on this slide Gruenberg-Kegel graph of this group. The second possibility, you can see condition on number P, R, S, and N. And this possibility realized for groups following shape. And you can see Gruenberg-Kegel graph of this group in this slide. So the second case, S is a solvable radical of G, is equal to or P of G, Q equal to, and G dash is L to P. And you can see conditions on numbers P, Q, R, S on this slide. And this case realized for the group of such form. And in this slide shows Gruenberg-Kegel graph of this group. The last case of this theorem, S of G is equal to OP of G, Q equal 3. Then there are three possibilities. The first possibilities you can see on this slide realized for groups, for direct products, cyclic group of order P and PGL to 9. And Gruenberg-Kegel graph of this group you can see on this slide. The second possibility realized for following shapes, for groups of following shapes. And you can see Gruenberg-Kegel graphs of Gruenberg-Kegel graph of these groups. So the last possibility realized for the groups of such forms with following condition on number n. And you can see Gruenberg-Kegel graph of this group for n equal to 3. So now I want to tell about short results. Let G be a finite non-solvable group. Q divides order of S of G, and the graph gamma of G as abstract graph is isomorphic to the pole. Then there are two cases. The first case, Q does not divide order of G dash, and normal structure of G you can see on this slide. For this case, there are 5 possibilities. The first possibilities realized for a group following shape, and you can see Gruenberg-Kegel graph of such groups. So the second possibility realized for a group of following shapes. And in this slide shows a Gruenberg-Kegel graph of these groups. So the third possibility is realized for a group following shape, and you can see graph of this group. Fourth possibility is realized on following groups, and you can see Gruenberg-Kegel graph of such groups. And the last possibility realized for a group such forms, and you can see Gruenberg-Kegel graph of this group of this slide. So the second case is Q is a Mersenne-Offermayer prime, and condition on numbers Q, P, RS, and normal structure of G you can see on this slide, and this case realized for following groups. Following group, and you can see Gruenberg-Kegel graph of this group. The last result, let G be a finite non-solvable group, and the graph gamma of G as abstract graph is isomorphic to the pole with vertex of order 1 less or equal 3. Then 3 divides order of G. There exist two possibilities. First possibility, G is a group without elements of order 6, and the second possibility, G dash is equal A 5 or S5, and condition on numbers P, Q, R, S, T, you can see on this slide. So each of possibility realized. Possibility 1 realized on all examples from theorem 2, and possibility 2 realized on group with such normal structure, and you can see Gruenberg-Kegel graph of these groups. That's all. Thank you for your attention.
Okay, thank you very much, Nikolay, for a very nice talk. Are there any questions to the speaker? Well, I have one small question concerning theorem 1. So actually, I'm not sure that I understand correctly the meaning of some notation you use. Well, where is it? So theorem 1, yeah, theorem 1. Well, okay, 2t factor, or you also use 5t factor. What is the meaning?
Repeat, please, question.
Well, I'm just asking about the meaning of notation you use. 2t factor, what is it?
Then I use standard notation which we can find in atlas of finite groups, and this is direct product, semi-direct product. G dash is quotient group G by S of G. Out is group of automorphism of group.
Okay.
In this case, Suzuki 32. And this is.
Sorry, can I make a comment?
Yeah. Okay.
Really, the group G has solvable radical and upper almost simple group, and this solvable radical has T factors, and some they of course are P groups for some P, and some of them are two groups, and 2T factor is a T factor inside of solvable radical, which is a two group.
I see. Okay, thank you, Natalia, for your comments. Yeah. Okay, are there any other questions to the speaker?
I would like to say something.
Yes, yeah, sure, of course, Anatoly, yeah.
Well, because I so co-author.
Yeah, sure.
We study a small graph, yes, 4 vertices. But this graph is very interesting, and the work with Gruenberg-Kegel graph of such type is hard, because general theorem of Vasiliev in this case does not work.
Oh, I see. I see.
And we look a new methods to work with Gruenberg-Kegel graph. And we have some interesting methods for this case.
I see.
I think.
Good, yeah. So do you mean that this method will be applied for the last case?
Yes.
Because Nikolay said that there is one open case, right?
Yes, yes, yes.
I see.
We use also the modular representation of simple groups. This is very hard theory.
Right, yes, that is true, yeah.